All right, so let's try to start solving this equation. And this is the differential equation we are solving. We need two things in order to put it into computer, right? Computer now can do a lot of things, but it still can't translate a physical problem into something a computer can solve. So even though computers can do a million things, I think human is still very required to translate any problem, any real problem, into something computers can solve, translate into a mathematical problem. So this is, we have completed the first step. Now from the differential equation to something computer can actually solve, there are two remaining steps. One is to discretize it. A differential equation is infinite dimensional. Computers have finite memory, so we need a finite dimensional version of this differential equation. And then the finite dimensional version of the differential equation is going to be a set of nonlinear equations. Then we need to figure out how to solve the nonlinear equations. So step one, discretization. So I'm going to repeat very fast what we ended up doing last time. We are going to introduce two more variables we call fp, and that is defined as f prime, and fpp, that is defined as the derivative of fp, or f double prime. And the third derivative of f is basically the first order derivative of fpp, right? And that is approximated as a central difference on a half grid point. So this is approximated as fpp at I plus 1 minus fpp at I divided by delta eta. Right, that's our finite difference derivative. This is approximated at grid I plus half, right? Or at the middle of grid I and grid I plus 1. Now we are also approximating f, as we also need approximation at I plus half, right? So we are going to be approximating the product of f and f double prime as the average of fi plus 1 times fpp I plus 1 plus fi times fpp at I. This is called the trapezoidal rule. This is approximating the value of this product by the average between the values of the product at the end grid points. That's kind of an average over this cell. So this is also at grid point I plus half. So these two terms added up should be 0 at every interval, right? So this has to be true. So the first equation we derived is fpp I plus 1 minus fpp at I divided by delta eta has to add this same term here is equal to 0 at I equal to, let's start with 1, etc. to n. N is the total number of intervals. The total number of values should be n plus 1, because we need an I plus 1 here for I equal to n. Okay, so this is the first equation. And the second equation and third equation are just copying these definitions. For example, the second equation is going to be f I plus 1 minus f of I divided by delta eta. That's an approximation of f prime. Has to equal to fp, which I write as subtract fp, also at grid point I plus half. So fp of I plus 1 plus fp of I has to be 0. This is an approximation to this equation. I'm just going to write as b, c. And this equation I'm just going to write as a. All right. So equation c is practically the same as equation b, but instead of f, we have fp. Instead of fp, we have fpp. Alright, so we have now these three equations. They are not just three equations, they are actually 3 times n equations because there is 3 equations for every I. So we have 3n equation for how many unknowns? 3n plus 3 unknowns, so we're missing 3 equations. These are the boundary conditions, right? So f1 has to be equal to 0, that's f0 equal to 0. When I is equal to let me just write down our discretization. So this is in the eta space. This is eta equal to 0, right? And my grid point I equal to 1. This is I equal to 2. And the spacing between them is delta eta always. So this is I equal to n. We think of that as almost infinity, something big, right? Etc. So this is I equal to 3, this is eta equal to 2, delta eta, etc. So f1 equal to 0, and fp1 is equal to also 0, right? How about the f prime infinity equal to 1? Well, this is actually I equal to n plus 1, because we have n plus 1 values. So how about fp at infinity equal to 1? fp of n plus 1 minus 1 is equal to 0.